Welcome to Season 3 of the Soundstage Audiophile Podcast. Last year, host Jorden Guth got a crash course in the fundamentals of hi-fi from enthusiasts, journalists, manufacturers, and music industry professionals alike. And those lessons will continue, but this year, Jorden will also get a history lesson from the legends who were there from the giddy-up and who made hi-fi what it is today. So with that out of the way, here's Jorden and this week's guest.
Hello and welcome to the Soundstage Audiophile Podcast. Today we're here with Peter Schuck, the Director of Special Projects at Anthem. Peter is one of the pioneers in computer technology and audio and a major force behind a lot of the different technologies, such as Anthem Room Correction, ARC, that we take for granted today. So welcome, Peter.
Hi, Jorden. Thanks for having me on the show.
Thanks for coming on. There's a lot that I'm super curious about with your history in audio and how you were part of the Athena project back in the day and your research and all of that. But before all of that, my understanding is that you have a degree in math. How did that influence you and bring you into audio? Like, did you have a natural interest in audio and that's why you went the math route, or kind of bring me back and tell me how this all kind of evolved for you originally?
Yeah, when I was in high school, I was always interested in music and recordings, and had a record player, bought lots of albums, spent a lot of time listening to stuff. Had several friends that were into that, and also were playing in, they had the band, and I spent a lot of time doing the sound for the band, like the panels and setting things up, sort of the technical parts of it. And spent a lot of time in high school in electronic shops, learning all about tubes and tube amplifiers and things like that back in the day when really transistors were around. But we had a radio operator teaching the course who was a radio operator from the war. So he was really into tubes. And it turns out that you can learn a lot from tubes and the way tube circuits work and things. And then in university, I kept that up as an interest. And when I was finishing my bachelor's degree, I was looking to do a master's degree, a special program called Master of Philosophy at Waterloo, where you do an industrial project. So instead of doing a thesis that's sort of totally could be totally obscure or something. I wanted to do something abstract. I just wanted to do something that had a real application. So I was looking around at various professors there and their research interests, and I found Dr. Lipschitz and Van der Kooi, who were starting up this audio research group. And they had one student in the past, and I went and talked to them, and they were doing a lot of interesting things on amplifiers and measurements, acoustic measurements, using an FFT box, which was one of the very early ways of having a digital measurement and time-gated instead of using an Annecord chamber. So I went and talked to them and decided that that's where I would do my master's. And we looked around at various Canadian companies at the time, try to find a partner so I could work on one of their, something that had to do with their interest. And that was an unfortunate time because lots of economic problems. This is back in 1981 where there was a bit of a downturn. So we did a lot of talking to companies, but it was kind of hard to get anything started. And eventually I found audio products in Toronto that they were like Energy and Mirage were their big brands. And I worked with them on doing a program for the design of crossover networks using a personal computer, because not many companies, especially small audio companies, even had anything like a computer. Like everything that back then that was being done was on paper, right? So, there were no computerized records or any of that sort of stuff in small companies.
Yeah, the personal computer wasn't really even a thing at that point, was it? It was probably mainframes and...
it was mainframes and mini computers, but the IBM PC had not quite come out. So I actually did that work on a Commodore PET.
Oh, nice.
Which is almost like a 64. But anyway, it was a little box with a CRT screen and a keyboard. I think it had 64K of memory, and
Massive.
it had BASIC in ROM, and it could read floppy disk. So you could write a program on the floppy disk and load it in, and it had to be like interpreted BASIC, so it was slow as molasses.
Oh man!
So that's what I did this thing on. So that means that when you're doing like a fancy program that's going to take measured data points in and measured or a crossover design, component topology, capacitors, resistors, and then do some kind of optimization, you got to really look for a good method. And all the equations turn out to be very nonlinear. So it was a lot of work. But at the time, we'd be running optimizations with, say, only 5 or 6 crossover components, and it would basically take like a day, sometimes 2 days, just to get to the end point and see whether you were going in the right direction. So it was quite painful.
And I can just imagine, like, just for reference, something like if you were to do the same thing today, would that be pretty much instantaneous?
Yeah, more or less.
Okay.
Even the current versions of ARC, do way complicated stuff, and actually a similar equations down below somewhere because you're designing networks. And it's like a fraction of a second, and it's instantaneous. Yeah.
It's wild to think of. And I was born in the 80s, right? So I don't have the extreme history with the kind of pre-computer age, but there's an appreciation there because I take it for granted every single day. Right now I'm wearing noise canceling headphones. I listen to audio on really great systems that use different stuff like ARC. And I take it for granted because I just was never around when that wasn't a thing. Sorry, I just had to put that in there because it's crazy to think like 60K storage is just wild. So from there, you started this project. The company that you mentioned is no longer around. How did that kind of transition? So
in the end, for that particular with that work, it was sort of like a co-op thing. We ended up designing the crossover for the Energy 22, which got a really hot reputation, and that speaker was around for many, many years. It was, there was obviously a lot more to it than the crossover. I mean, the driver was the tweeter was pretty unique, and the way they had to do the surround on the polypropylene woofer and all that sort of stuff. But that was pretty successful, and eventually that company got bought out by another company, Global Sound, and eventually they kind of went buns up fighting patent lawsuits, where they won the lawsuit, but the other side couldn't pay the damages. And anyway, that sort of ended up. But after I finished my degree, I was looking for something else to do a PhD, and I determined that after that experience, that the audio industry couldn't really afford to have not many places you could get employment, right? As a researcher or as a fairly advanced stuff, that it's just there were only a few companies in the world that were willing to move in that direction, that were spending that kind of money. It's not like it is today where everybody is interested in active noise cancellation and the little speaker pods and voice identification. Back then there was none of that stuff. So I ended up looking around and deciding that Canada's a big country with oil sands. So I did my PhD and basically in looking at some problems in oil sands. So I'd gone to Western, and did more, numerical analysis and mathematical modeling of stuff that happens in oil fields. And so that was graduated in 86. But then when I was writing up my thesis and, getting ready to exit and look for the next step in my career, it turned out there was a bit of a dip in the oil patch in Canada. Yeah. And so there weren't a whole lot of jobs there. And I also, put in a lot of applications to universities for becoming a professor. And at the time, I did mostly computing and numerical analysis. And there were a lot of universities wanting to start up computer science departments because the only one that existed was Waterloo, and the only one pretty much the first and only in North America. But they all kind of so they didn't really like the idea that I had a PhD in applied math. So I went to interviews, but it didn't look that promising. And then I had applied to the NRC for a postdoctoral fellowship. And out of the blue, I get this call, and it's Floyd Toole. And he says, well, I got the funding to get a postdoctoral fellow, and how'd you like to be do that? And I had done this application, 6 months before that, and I had no expectation of getting a call from NRC because they have thousands of people applying for, 5 or 6 fellowships every year.
Yeah.
Anyway, I went to Ottawa and hit it off with Floyd. I had met him once before at some conferences, talked to him, and, because it was yet another Canadian connection with our research group in Waterloo that, people audio community is a pretty small community, but it's lots of people. Everybody knows everybody, and everybody kind of knows who the people are that are doing good work and are worth reading their papers of. So I ended up accepting the position at NRC.
And this position at NRC, was this specifically for the Athena project, or was this unrelated?
No. This was in the acoustics and signal processing group.
Okay.
They had just been renamed, and Mr. Mulrooney had just decided to cut 20% of the employees at NRC, and I happened to be one coming in. And then the winds kind of blew because I was supposed, original idea was I was going to go in and work with Floyd in this group on, audio related stuff. And not too much later after I got there, they decided that they needed someone to look at active noise control. And there was nobody there who knew anything about or was totally excited about digital signal processing. So they said, hey, new guy, you're the guy. So I kind of split my time between working with Floyd on some experiments he was conducting and then re-equipping the anechoic chamber because it had old B&K strip chart recorders and very old school kind of stuff. And then they had purchased a new Amber box, which was a Canadian company in Montreal that did sort of a digital measurement system. So instead of an analog sweep, it was a digital step tones, and it had like an A to D, and you could, get the actual numbers in a file, right? Rather than looking at a little line on a chart. So that system needed a controller. Like we hooked it up to a PC, and then I wrote all this code to talk to it and control it and do all the standard measurements that we thought we should do, and do all these calculated curves that Floyd is famous for, the 15-degree window and the 30-45 window and the half hemisphere and the full hemisphere and totally radiated power and the directivity index and all that sort of stuff, distortion curves. and also did some automation for some psychoacoustic experiments we were doing. And that was sort of my pet project on the side. And then on the rest of the stuff I did there was all looking into active noise control and trying to set up the first thing I was working on was a active noise control in a duct. So you have two mics, an upstream and a downstream, and noise source, and you're trying another speaker to cancel the noise, and you're trying to make it quiet or reduce the noise. Basically something like your active headset, which is very much the same. There's two mics and there's feedback and feed forward, and you're in a controlled space.
And so at the time, like when you're doing this experiment, was the idea to commercialize that technology, or was the idea to solve, like, was there a problem that you were looking to solve, and that's why you started going down that route?
So the impetus was more that the powers that be had pitched that project as a very important new field in acoustics that was going to become really important. So we needed to have some knowledge about it in Canada, and so we could potentially do something with industry. So the simplest thing was that type of an experiment in a duct, so that we could get some experience on how this thing worked and what we needed to do to get it going. There are lots of applications, potential applications that were being written about at the time, like reducing noise from a smokestack or reducing jet noise. There were lots of, in our group, there were people that were working spent a lot of time on berms and highway walls type things to reduce noise from highways or to reduce noise around airports. And the issue always is at low frequencies, the wavelength's really long, so it tends to crawl over top of those kinds of things. So it's very hard to passively attenuate low frequencies. So active attenuation using anti-sound has got a lot of problems at low frequency, because the phase tends to stay the same of the wave for quite a bit of period of time. Like if it's 20 hertz, you have like 50 milliseconds between cycles, right? So when it's in a peak, the acoustic waves in the positive, it's there for a long time. So if you pick it up with a microphone, you have a lot of time to
do something about
it and anti-sound it, right? Bring it out in the reverse phase. Whereas on high frequencies, the wavelengths are so short that where you try to cancel it, the phase may not be the same as where you're picking it up.
Interesting.
Right? And the distance between your ears, your head space is about effectively half a wavelength at a kilohertz, roughly, right? It's about 6 inches or whatever. So that means that if there was a null at one ear, there would be a peak at the other, right? So if you tried to cancel something, right, it's going to get hard, because you're going to have to do two different things.
I've never really thought about that.
Different at both parts of the ear, right? So that's why, if you have a 1 kilohertz tone playing in a room continuously, it's hard to tell where it's coming from, because the two ears are hearing different phases. If you turn it on suddenly, you get this wavefront, and yes, you can tell that helps you localize it, right? Because you get a interaural time difference and interaural intensity difference for a very temporary period of time. But once the standing waves build up, it's really hard, because one ear is in the peak, and whatever. There's huge phase difference.
Interesting.
So in any case, so there was a lot of interest in that field and with active noise control, and there were like patents. Everybody was taking out patents. It was just a horrible field at the time, because if you actually wanted to do anything, you'd be banging your head against all these patents everywhere. And then there were companies buying up patents, patent attorneys just collecting patents for, because most of it, you couldn't really, there wasn't a lot of hardware around to actually do it in for real, right? You'd have to build analog circuits and try to do it. Wasn't a whole lot of, there weren't a lot of DSPs when I started. There was like the very first TMS 32010, which was like, I forget what the speed was, but it was like, it had about 2 memories of 256 16-bit words, I think, and a bit of for data space, and I forget, maybe 1K of memory for program, and it was really minimal.
And I think we kind of previously we quickly chatted about this, the idea that you were able to do a lot of the research, but you had to wait for the technology to kind of catch up before you could implement some of your findings and some of the things that you believed would work.
Yeah, a lot of people, you could write, there were a lot of papers around and ideas about a lot of the stuff that was very applicable was the inactive noise control when you're in an enclosed space like a room and you want to cancel frequencies. Then, people showed that the best way to do it was to put like speakers in the corners, because then it would excite all the standing modes in the room, and then you could sort of get some kind of global control of a sound field in the room, or at least close to it. And when you think about audio, well, you actually want to do the same thing. You want to control the sound, except you don't want to make it zero. You want to make it the desired music.
Yeah.
Right. So a lot of that work, kind of applies. What doesn't apply is that when you have a adaptive system, which typically these people were looking at adaptive filters, so they move around. When it's noise, you want to cancel the noise, but all you're trying to do is, in the end, your result you're looking for is, say, a 20 dB reduction in the noise. But then that means there's still noise. And so the noise that the adaptive filters are causing, because they're moving around all the time trying to adapt to the signal, doesn't really matter, right? It's hidden in the other noise, which is the noise that's left over, right? But when you have audio and you start having adaptive filters, you have to freeze things, right? You have to slowly change the filter. Otherwise, you get filter noise.
Yeah.
Right. You're going to get,
you start distorting the sound, and the whole point of it is to enjoy the music, or enjoy the sounds, not necessarily remove them.
Yeah, it's sort of akin to, in the early days of digital studios back then, digital consoles like zipper noise, where they would ramp the volume up and down, say like an analog volume control, you just turn a knob, right? Well, if you do that digitally, and since you have to make discrete steps, you get this kind of zipper ticking noise as you're turning the volume, right? And then some of the solutions that were come up with is they used to have, and they still do, most of the DACs that are out there, they have if they have a volume control built in, they basically have a delay. When you tell it to change the volume, it waits for a zero crossing of this audio signal to change the volume, so that you get less
fascinating
noise, right? And it'll time out. The other way is, as well, as you can add dither or, do other things to average the sudden change in the volume, right? And it's because you're stepping into a discrete value.
I had no idea. That's fascinating.
So anyway, that was sort of the first couple of years at NRC. And then, we always had loudspeaker companies coming in, and even some American ones. And we had some interaction with THX and the design of their speakers for home. And Floyd got this idea that, he had done a lot of studies on what makes a good sounding loudspeaker, and having this whole system of doing blind testing, double blind testing, 4 speakers in an IC standard listening room, and then doing evaluations, having good music to use for that evaluation, and then sort of correlating that to the measurements that we were doing in the anechoic chamber and trying to see, okay, yes, the speakers that do well measure well. They are reasonably flat. They don't have tilts in their frequency response. The crossovers are well designed. The total radiated power, is fairly smooth. All these sorts of things. And we wanted to get to, what's the next thing and how can we disseminate that better? So he decided we kind of discussed a lot of trying to get the audio companies in Canada involved, like especially the speaker companies, into a project that would go to the next step and try to study what the interaction was between a loudspeaker room and the listener, and how much difference does it make where you put the speaker and what kind of room you use, and then what can you do in terms of DSP to sort of mitigate that? How can you make the speaker sound more the same regardless of where you put them, and which room you put them into? It sort of came up that, we discovered from his listening test that it looked like there was, 4 positions, but it looked like speakers in position 2 always seemed to score a little. That seemed to be a slightly favored position. And so we sort of had a pretty good idea from measuring in the room that there could be a pretty big effect of the room affecting the listening test scores. So we went around to the various companies that we knew about and could find, and pitched this idea of setting up a consortium, which ended up being called the Canadian Audio Research Consortium, getting them to collaborate together, and because none of them had those sort of resources to do any of this kind of work. So if they all pitched in a bit of money, there would be some money, and NRC could pitch in some money and provide resources, and we could study this problem and maybe come up with some solutions.
Now, was that Project Athena or was that something else?
Yeah, that was Athena. Okay. So that was the start of Athena. It took like probably a year before it got off the ground. And then eventually the lawyers get involved, and like who owns what and all this sort of stuff. Like it was a bit of a nightmare, but eventually we did visit a lot of companies, and I think 6 companies decided to join in, and it was pitched as, I think, a 2 or 3 year, but anyway, it ended up being 3 years. Might have been the third year, it might have been a 2 year, and then we extended it for a year because we weren't done. And then a couple of companies dropped out because there's a funding issue and economy, I guess. So the project ended up being 3 years. Floyd was there till 91. Then he went off and offered a job at Harman and left. So I was kind of the NRC employee on this. We had up to about 10 people working on it at one time.
Oh, wow.
It was kind of split in half, maybe, or pretty much in half, where half the people were working on psychoacoustic experiments, so experimental side, running people, listeners through tests, various experiments, and half of us were on the building a DSP box and developing DSP methods. So anyway, so I can go over some of the things we looked at if you want, or
I would love to. I would absolutely love to. I think there's a lot that we could still explore in terms of the specific stuff that you were working on for the Athena project, in terms of the DSP, and then how that kind of led you effectively to where you are today. So I'm gonna pause it there for just a moment. We're going to take a quick little break. And then when we come back from the break, I think we can jump into some of the additional stuff that you were doing at NRC and how that kind of led you to what you do today. Welcome back to the Soundstage Audiophile Podcast. I'm super curious, Peter, as you're going through this Athena project, as you're learning all of these different things, what is the feedback that you're getting that you're then taking and applying that to make changes to kind of document those results? Like how are people kind of expressing their feelings or their preferences for you to then document them and say, okay, this is an established baseline of what we know works based on this amount of people?
This is really one of the cruxes of doing listening tests with people as subjects, is how complicated a questionnaire can you get them to fill in? How much training do they have in terms of being able to identify differences? Everybody has sort of this is what I expect something to sound like. And then also, can they hear things? Are they a reliable listener? Okay, so very quickly, in the past, they had used a 0 to 10 scale of fidelity scale at NRC. That was what Floyd had used, and trying to explain to people off the street who we basically just put ads in places and bulletin boards and trying to get people pay them money to come in and do listening tests, be a subject, right? And trying to explain to them how to, this 10-point scale and, what fidelity is and that sort of thing. It's really, really difficult. And it's really difficult to get answers. So, there was a different project in Denmark where they spent enormous amounts of time. They were doing similar kinds of experiments with subjects, training the subjects to okay, this is what a resonance sounds like, at this frequency, at this much, and then, just training them and getting them consistent. And we decided not to go that route. So instead, we came up with this 5-point preference scale. So instead of telling the people, which sounds truer or which has got the best fidelity, we just ask them, which do you like? What's your preference? All right. Is your preference, so for, comparisons where the typical test where you had 4 speakers behind a screen and you're asking them to evaluate things, we just ask preference questions on a 5-point scale. Much simpler, and it seemed to give us very similar results. We got, for 80% of the people could do the test. So effectively, when you do do repeats and you look at the statistics and the power of an individual listener's statistical power of their responses, you could see that they were being consistent.
Interesting.
And then we would have the 20% of the people who they were random. Like, you're just looking at it going,
what's the opposite of golden ears?
They would be just like, either they weren't taking it seriously and just wanted to get paid, or they just couldn't hear the differences, or mentally they may have not had a way of
distinguishing the differences?
Yeah, distinguishing things, or not everybody likes music, I guess, or whatever, right? It's like some people have perfect pitch, and most people don't.
Yeah,
and maybe some people just can't identify a melody.
So,
right? Or
for the audio that's being played when they're listening to it, is this their preferred audio, or is it the same kind of tracks that you're using across all people? How?
Yes.
Okay.
Yeah, this latter. So we picked a track. So this is critical that you pick well-recorded tracks that have good dynamic range and wide spectrum. Otherwise, you're not really testing the speaker.
Okay.
Right? If I put in like a telephone conversation kind
Good
of
luck.
bandwidth, on a bunch of speakers in a room, it's going to be hard to tell which one has any bass and which one doesn't, and which one is really bright and sibilant, because there's nothing to test that.
Yeah.
Right. So you have to make sure that the content is good listening content. Right. It's also got to sound good, but it's got to stress the system. The other issue is, which you quickly discover, is there's some stuff out there that's really terribly recorded. And so you get back to this, as Floyd likes to call it, circle of confusion, where if it's recorded, say somebody's in a mixing studio and they're listening to a terrible set of speakers and making recording decisions and EQ decisions based on a very bad set of speakers, like Yamaha NS10s or something, and which used to be the thing, or on a boombox. There were people that were out there that would make the final mix by putting a boombox on the mixing console and listening to that, right? So, and that was because somebody mixed a hit record like that, right? The recording industry is super fickle, especially back then. They would find out that somebody mixed it on this console or this speaker or in this studio, and then everybody would want to try to duplicate that in order to make the next hit record. So if you have something which is overly bright in the recording because it was mixed on something that had no top end, then no matter what, unless you play it back on overly dull speakers, it's not going to sound good.
Interesting.
So you have to be really careful that you don't pick tracks that are poorly recorded or,
And how did you guys come up with the tracks that you ended up using?
Just doing a lot of listening and having tried them. We actually had experiments where sometimes we were naive and threw in some new music without doing enough consideration of that music. And at the end of the experiment, we would look at the results for those tracks and they would be all over the place. And the results for the other tracks were fine. And we'd say, okay, we're never using that track again. So, I mean, there were a lot of listening tests in the past, and, it's pretty well accepted that, there's some artists that are recorded better than others and some producers that do a better job than others. So it is definitely an issue. And it's, also can be a criticism of how things were done. So given that we tried to get these listeners to use this 5-point scale, which is much simpler. We didn't ask them for, what's the bass like? Well, a whole bunch of other questions that are just going to confuse them. And for those particular types of experiments with 4 speakers in a room, we could get the 95% confidence intervals on, between the speakers, and we could see differences most of the time.
That's wild.
If there were differences, right? And so the first thing, we focused on is, how much of a difference is there in the 4 locations in the room?
Yeah.
Right. So we did a lot of swapping, and we looked at the position of the speaker as a variable, and it turned out to be significant. at 95% confidence level. So, and it was when we used like 4 decent speakers that we knew were pretty good. Then it turned out the position variable was the same size or bigger than the differences between the speakers.
Oh, interesting.
Okay, so these are the kinds of things we had to do at the start. Is like, what's the point of fixing something if there isn't a problem, right?
Yeah.
You have to establish, is there really a problem and how big is it? Okay. So that was one of the first ones. And then we did the same thing where we had, I think 4 different rooms. We had a bunch of different rooms. And then so we took the same collection of speakers and did the evaluations across these 4 different rooms in order to see, okay, does the room make a difference? Not just the speaker location. And we could show that the room was a variable, right? Significant effect on this rating from 0 to 5. So we definitely had a problem. So then we looked at, okay, so how can we speed this up or make it easier or make ourselves more efficient? And so Sean Olive was the main runner of experiments and coming up with a lot of the ideas and for the listening experiments. So we took a KEYMAR that we had, because we had done lots of in the past some recordings with KEYMAR and played them back over a headset and like live recording in the room. And the imaging out of the KEYMAR is just amazing when you're sitting in the room with the headphones on and you're listening to a KEYMAR recording made in that position, and people are moving around the room while music's playing. You can hear it. I mean, you want to turn your head. It's so real, cool. Even though KEYMAR's head is not your head and your ears are not KEYMAR's ears and whatever, right?
Yeah.
It's pretty good. And so we did this experiment where we wanted to. So KEYMAR is a dummy head with microphones down the ear canal. It has pinna, and it has an ear canal, and then there's a microphone at the end, and you can record. So we did this experiment where we recorded the listening test of the same speakers that we were using in the same room in the same position on KEYMAR. And then we brought our subjects back and we had them do the same preference evaluation using the KEYMAR recordings over headphones.
Interesting.
And then we showed that we could get the same relative ranking of the speakers using that KEYMAR recording, as we had in the room. And we could show that the room position effect was still a factor, and it was very similar, and across rooms as well. So then we were able to do some experiments where we could do like an instantaneous switch between a single speaker in multiple rooms. So we could do an experiment where the 4 things you were listening to was the same speaker in 4 different rooms.
Huh.
Right.
To see how that
track
impacts the overall preference.
So because you can't move yourself that quickly between those rooms, right?
Sure. Yeah.
And there is your auditory memory is not very long term for small differences. So it's really hard, you couldn't run back and forth between the rooms and do that evaluation and kind of expect to get anywhere.
Yeah.
But when you can do instantaneous switching between those 4 tracks, say from 4 rooms, and they're all synced up, then it's different, right? You can potentially do experiments like that. And then we did that, and we could show that, yes, the same speaker in the different rooms was actually you could change the ranking. You could change its score.
Now, as you're doing these different experiments, is there moments where you're able to say like, hey, manufacturer, start changing this? Or, hey, I'm going to go home and I'm going to switch out the way that I have my room set up. Are you taking some of these lessons and instantaneously applying them? Or is that more of a kind of wait to the finale, wait till everything's all said and done?
I think it was more, I know that people who were doing this had, some room treatments they had done, were doing at home and things like that. Yeah. Not so much, where you put your speakers is usually pretty constrained by your decor.
Sure.
And, as long as you're willing to move them away from the walls and things like that, like the obvious things, and then putting in maybe some treatments if you think that's a problem, if you got a bad reflection or something. But we were specifically not, like, we were using, one of the rooms we used was the IEC room, which had a bunch of membrane absorbers in order to meet the IEC standard for low frequency reverberation. Okay. But the other rooms were not. They were just gyprocked. They were reverberant. Okay. We didn't want to base our whole thing on, well-treated rooms and all that. We wanted a typical, like a real room, right?
Sure.
With real furniture and pretty live.
Well, then I'll ask it this way, and this might segue us into kind of your next career change. Were the lessons you learned then percolating in your mind as things that you could apply or use, let's say, math or kind of the technology to apply to correct for that on an ongoing basis, a la maybe Anthem room correction, let's say?
So yeah, we were, so on that, based on those experiments, we knew, let me go a little further along the road here.
Sure, yeah.
Based on those initial experiments, we knew we had established that there was a problem and that needed fixing. Okay. So once we had established that, we were trying to analyze, like, what are some of the fundamental things that are happening there? And so we started doing some more basic experiments. We looked at the audibility of resonances. So we ended up writing a big paper on that, looking at, the frequency and Q of different resonances that, like, what are the things in the room that could be causing changes? So one of them is resonances in the room, right? Other things are reflections. And I can get into some of that later. But so we looked at resonances as one thing. So we did all these experiments where we artificially added a resonance either to headphone recording or to a room loudspeaker kind of listening test. And we did like a technique called two alternative force choice up-down testing, where the person is listening without the resonance or with the added resonance, the listener, and they determine whether or not there's a difference or not. Right? They listen to something and they say it's the same or different, and so they either got it right or wrong because they don't know if it's with the resonance or without. It's like ABX kind of test. And then, so if they get it right, you reduce the level of the resonance and you repeat. So if they get it right twice, you drop the level. If you get it wrong, you up the level. And so eventually, you end up at a level at the person basically going at a steady level where it's just going up and down by one. Yeah. And that's considered the 75% threshold. Okay, so that's a little, because you have to get it right twice and wrong once, it's a little higher than a 50% threshold where you're only getting it right half the time. But it's an easier level to establish. It's an easier test for the people to do. So we would do that and then sort of establish, okay, if at a certain frequency, what's the cue of the resonance before you hear it? And 70% of the time. And then we looked at different frequencies. And it turned out at low, and then we looked at anti-resonances, dips, okay? And it turned out that the dips are much harder to hear than the peaks, except when they're low Q, meaning that they're wide as opposed to narrow. They're about equally, a small peak and a small dip is about equally difficult to hear. But when they get to be narrow, like the typical, if you look at a room curve, room measurement curve, you get all these really narrow peaks and dips. The peaks are much more audible when you have content at those frequencies because it's much louder, whereas the dips are much more difficult to hear. So we did that kind of work. And then we also looked at all pass phase. So when you look at a measurement of a speaker in a room from the speaker to the mic, the transfer function, it's basically a peak, first arrival, and you see all the reflections and then a decay. So if you wanted to design a filter that makes that a perfect impulse so that it would be perfectly flat and everything, you would need to invert that measurement. So you can basically look at that as a system, and whether or not you can invert it depends on whether or not it's minimum phase, because that's just a concept. But basically, to invert it, you have to have a filter which is like 1 over the original impulse response. And if it has any, all pass zeros anyway, if it has a certain characteristic, that means when you try to invert it, it's unstable. And it would just basically ring forever. And it turns out that all these room curves are non-minimum phase and are not invertible. So you can't make a perfect inverse. You can do an approximate inverse by having a time delay. And so delaying and then having like a pre-ringing filter, like an echo where the filter starts before the music and then whatever. So you can try to do some kind of approximate inverse. And then, so we did experiments on that. And how much of a ringing could you tolerate? Because it's well known that you have a lot of backwards masking, but not forward masking. So if you look at an impulse or some kind of a sound and you look at the echo and you look at where the threshold, when can you detect that there's a difference, that there's an echo there or not? It can be pretty loud and pretty far out when it's after the arrival, before you can hear it. But if you put that little blip before the main signal, it turns out you can really hear it. And you haven't got a lot. You got basically maybe a millisecond or a millisecond and a half of time that you can have a pre-ringing filter or a echo, a pre-echo.
Peter, there's some absolutely incredible information here, and I think there's still a lot left to be said. So if you're okay with it, I think it would be a good place to kind of stop this episode. And what we can do is kind of do our second half of the conversation in another episode where we can get into life after the Athena project and where that's kind of led you. How does that sound?
Great.
Awesome. So with that, everyone, thank you, take care, and we will be back next time with a continuation of Peter's conversation.